that if you start with a unitary theory in Minkowski, then you get a reflection positive theory in Euclidean. But of course you can check, sometimes you can check reflection positivity directly in the Euclidean without going through the peak rotation. So this is useful to keep in mind. So for example, if you have 3D Ising model just on the lattice, then it's not difficult to check that it's reflection positive. So the way you do it is, so as I said, we have reflection positivity means that certain correlation functions, two endpoint functions, where you insert points symmetrically with respect to a plane, are going to be positive. So let's take the Ising model on the lattice, and we want to show that this correlation function is positive. So this correlation function is given by, let me write it as a path integral, but it's a discretized lattice. So I have a path integral. So there is a bunch of operators inserted at, let me denote it collectively, inserted at positive x1, and then there is a bunch of operators inserted at negative x1, and then we have e to the minus s. So what you can now do, you can split this path integral into, or integral over spins, into spins which are located at the surface x1 equals 0. Let me call it phi 0. And then you integrate over spins where x1 is bigger than 0. But here you impose boundary condition that phi of x1 equals 0 has to be equal phi 0. And here you insert x1 positive. And the action you split into two pieces. So the one which corresponds to the upper half plane and one which corresponds to the lower half plane. So e to the minus s plus, so s equals s plus plus s minus. So you have this, and then you have the same thing with x1 negative. And again you impose the boundary condition. But now you notice that, at least for the Ising model, it's obvious that these two factors, provided that you insert fields symmetrically, they're identical, because you have symmetry, which relates the two half planes. So what you have here is just an integral over the boundary conditions on the plane of a square. So of course this is going to be a positive quantity. So this integral over square. So this argument shows that the Ising model is reflection positive on the lattice, and consequently it's going to be positive also in the continuum limit. So the CFT that is going to describe the Ising model critical point is also going to be reflection positive. Okay, but of course, it's nice that many interesting CFTs are reflection positive, but there are also some physically interesting theories which are not. So let me give you some examples. Can I erase this? So example of a non-reflection positive theory. So let's take theory of elasticity. By this I mean a theory which has a vector field u mu, which you should understand that you have some elastic medium, and u mu is a vector of a local deformation of this medium, and the action, the Euclidean action that I'm going to write down, is just the energy of the elastic deformation of the medium, and it can have two terms consistent with rotation invariance or with crystalline symmetries. So there's going to be, okay, let me write it, alpha d mu u nu squared plus beta d mu u mu squared. So this is the energy of elastic deformation, and so this alpha beta are related to the elasticity moduli, and of course we have to demand that the energy of deformation is positive. So there was a question last time about the positivity of Boltzmann weights. So the condition for positivity, so demanding that energy is positive for whatever deformation, you can check that it's going to happen if alpha is positive and alpha plus beta is positive. So let's impose these conditions. So now let's put our elastic medium at some finite temperature, and then we can measure correlation functions, so of statistical fluctuations of this medium. So we can measure things like, for example, so we are going to be dealing with the partition function of S over T. And we can measure correlation functions, u mu, u nu. So it's a free theory, it's a Gaussian theory, so this correlation function is trivial to determine. So it's trivial to determine momentum space just by doing Fourier transform, and then you do then you can determine it in coordinate space. So this is just some exercise. This is actually an exercise. The first exercise is to determine this correlation function, and then once you determine this correlation function, then you can do two more exercises. So you can check that it's not going to be a reflection positive. So this correlation function is not going to satisfy reflection positivity. And once you check this, you can do another exercise. You can think about what goes wrong if we try to run the argument. So I gave you an argument for the Ising model. It was a very simple argument which showed that the Ising model was reflection positive. Here I also have a theory with a local action. So it's not a problem to take the section and split it again into parts, one for the positive, one for the negative half space. So the only difference is that here we have a vector field, while for the Ising model we had a scalar field. So think about, why if you run the argument for the Ising model in this case, you cannot show analogously that something is going to break down and you will not be able to show that it's positive. And indeed, by checking the two-point function explicitly, you can see that it's not reflection positive. And once you have this two-point function, you can do very easily another exercise, which is, so is it scale invariant? So is this two-point function satisfies scale invariance, and is it conformally invariant? So it's actually anticipating, you will discover that it's not conformally invariant. So this theory of elasticity gives an explicit physically relevant example of a theory which has scale invariance but not conformal invariance. So now let's go back to CFTs. So this is a counterexample, but there are many theories, there are many relevant theories which are unitary. And so let me give you just a list, just to keep in mind. So as I explained, 3D easing is going to be unitary or reflection positive. I'm using it as synonyms, is unitary. ON models are also going to be unitary by the same argument as the 3D easing. Now, if you take any conformal field theory which describes a quantum critical point of a physically realizable material, is also going to be unitary, because quantum mechanics in nature is unitary. So any quantum critical point, if it is conformal, if it is rotationally invariant, if it has Lorentz invariance, then it's going to be unitary. That's clear. So non-unitarity can thus be relevant only for critical points of statistical physics models. Like here we had theory of elasticity, and there are other notable, so these were unitary, but there are other notable examples which are not unitary. For example, if you consider self-avoiding walks, for those who are familiar with this, so self-avoiding walks, they have a statistical physics model which has a critical point, and it is not unitary. And the way you understand this is that the self-avoiding walks, if you're familiar, you remember that it can be obtained from ON models by taking the limit of n going to 0. It's n going to 0 limit. But this limit n going to 0 is going to destroy the unitarity property of ON models. So ON models are unitary only for integer values of n. So if you take if you go through the non-integer values of n, and in particular take this limit n going to 0, then this destroys the property of unitarity. So that's one way you can get non-unitary theories, through this kind of non-physical limits. Another way you can get non-unitary theories is by turning on imaginary couplings. That's a more perhaps intuitive way. So for example, you can take imaginary couplings. For example, you can take the easing model and you can put it in an imaginary magnetic field. So that's physically this may look as an absurd thing to do, but mathematically it's an interesting question. And actually it's known that if you put the easing model in the imaginary magnetic field, and if you fine-tune the value of this magnetic field, then you can reach a critical point. This is known as a Lee-Yang critical point. So there is a CFT which describes this critical point, and this CFT is not unitary. interpretation is different. So because I don't put a quantum mechanical model with imaginary coupling, I put kind of a classical statistical mechanical model, consider the partition function, and I just analytically continue the partition function to the imaginary values of parameters. So I still have an equilibrium, but I don't have positive Boltzmann weights. I have complex Boltzmann weights. So it's you say it's going to correspond to having dissipation. Well, dissipation does not just reduce to imaginary couplings. It's yeah. No. Well, it's an interesting question, but I must admit that I haven't thought about this correspondence. So let's discuss this after the lecture. Okay, but then, so keep in mind, there are non-unitary theories. It's interesting to think about them, but I'm going to focus on the unitary theories for the rest of this course. And assuming unitarity, so what is it going to mean in practice for, if you are interested in doing conformal bootstrap? Well, in the end, the consequence of unitarity are going to be that operator dimensions in unitary theories are going to satisfy certain bounds. So unitarity bounds on operator dimensions in CFTs. So these bounds, these are lower bounds. So dimension of any primary operator is going to be greater or equal than a certain minimal dimension, which is going to depend on the spin of the operator. And for scalars, so for L equals 0, this dimension is equal to d over 2 minus 1. So it's just the dimension of the free scalar field. So d scalars is greater than or equal to d over 2 minus 1. So it's very intuitive. If you have a free scalar field, you turn on any interaction in the unitary theory, the dimension can only go up. Any interaction only increases the dimension of a scalar field. So this is one property. If now if you consider with spin, then this unitarity bound is equal to L plus d minus 2. So in particular, for L equal 1, you get d minus 1. And for L equal 2, you get d. So d minus 1 is the dimension of the conserved current, and d is the dimension of the stress tensor. So what this bound says is that it's impossible, so that the conserved currents are the lowest dimension fields with spin 1, and stress tensor is the lowest dimension field with spin 2. Cannot have lower dimension operators. And okay, there is an analog of this for higher spins. So in every, if you raise the spin by 1 unit, then the minimal dimension also raises by one unit. So these are the unitarity bounds, and there are various ways to prove these bounds. I'm not going to give you the complete proof, but I'm going to give you, at least I'm going to explain you how to show this bound for the scalars. So this, for the scalars, it's really easy to convince yourself that this bound is true. Any questions about the statement of the bound? So let's take a scalar field. Let's take any scalar field of dimension delta. So I told you that the two-point function is going to have this form with some constant c. But now, you know, if we are in a unitary theory, then the two-point function must be positive, because I can put these points x and y, I can put them symmetrically with respect to a plane, and then this precisely should be reflection positive, so C must be positive. And in fact, I already said that by rescaling the fields, I can set the C to be equal to 1. So that's just what you already know. But now, you know, given this equation, we can consider, we can differentiate it in x and y. So d mu phi of x, d nu phi of y. So the, you know, just differentiate the formula in x and y. And, you know, again, we have to demand that this two-point function, now it's a two-point function of a vector field, has to satisfy reflection positivity, right? And what does this mean? So if we, let's put 2 points x and y symmetrically with respect to a plane. So if we differentiate in the same direction parallel to the plane, then this has to be positive. So this has to be positive if mu is equal to nu equals, say, 2. So this direction is 1, and let's take this direction equal to 2. If, on the other hand, I differentiate in the direction perpendicular to the plane, then remember that when we were taking reflection, when we were defining reflection positivity, there was a factor of -1 for every component perpendicular to the plane. So it has to be negative if mu equals nu equals 1. And in fact, by, you know, if you work out the derivative, then you will see that from this condition, you conclude that delta has to be non-negative. So you already learned something. You already learned that delta has to be non-negative, and this is going to be automatically satisfied. But you did not learn yet that delta has to be larger than delta 3. So you just learned that the two-point function should decrease at infinity. That's also a natural conclusion, but it's not yet what we want. So now, what do you think should we do in order to have a chance, have a shot at the inequality we are after? Any suggestions? What else can we do? Well, if you take mu and nu in different direction, then, you know, we can consider this two-point function, but reflection positivity does not put any constraints on it, because if we put it in different directions, then this is not reflection positive, nor not even if we, you know, for whatever sign. So that's yeah, that doesn't help. I'm sorry? Well, because, you know, if I differentiate orthogonally to the plane, then the symmetric situation is this one. So it means that I have to differentiate with respect to x in positive direction, with respect to 1 in negative direction. That's all. Yeah. So what other inequality can we try to impose? Trace. Trace of what? Yeah, exactly. If you don't know what to do, let's differentiate once more. So it's a very simple idea. So of course you have to differentiate more. That's you're absolutely right. And so in fact, you know, what's gonna work is that you just take a Laplacian. So let's consider this two-point function. So this is a scalar two-point function. There are no indices. Moreover, you know, even without doing any calculation, you already know that, you know, this once you take these derivatives, you are going to generate some polynomial in delta in the numerator. And already without doing any calculation, you know that this polynomial is going to have a 0 at delta equals delta 3. Because delta 3 is free scalar, it satisfies the equation box phi equals to 0, so this is going to vanish for free field. And so it's going to be some polynomial which you can work out, but it's going to be proportional to delta minus delta 3, you know, in times something, some other factors that you don't need for this argument. So it's going to be, of course, x minus y dependence here, x minus y to the power delta plus 4. So that's it. You know that if delta is smaller than delta 3, then this is negative, and we have a contradiction. So delta can only be larger than or equal to delta 3. And you know, since delta equals delta 3 is a physical possibility, you are not going to discover any other conditions but if you keep differentiating. So it's going to be the best you can do. Yeah, there's a way to argue, yeah. No, there is a, you know, you can yeah, you can construct various rigorous arguments that's the best you can do. So that's it. That's and by the way, and by playing similar games for fields with spin, you are going to prove these other bounds. That's all there is to it. And there's going to be another consequence of unitarity for the UPE coefficients, but I'm going to mention it later on when we will need it. Okay, so we already were discussing CFTs for quite a while. We learned kinematics, we learned unitarity, and now we have to finally learn about dynamical. So what is the counterpart of dynamical principle for conformal field theories? This is, so the role of such dynamical principle is played by OPE, by operator product expansion. So let me explain what this is. So we already know that if you take a 3-point function, so let's consider a 3-point function of 3 scalar fields, x1, x2, x3, and so we already know that this 3-point function is going to be equal in the conformal field theory to a constant f1, 2, 3, and now in the denominator we are going to have x1 minus x2 to the power delta 1 plus delta 2 minus delta 3. So let's write this all in painful detail. x2 minus x3 to the power delta 2 plus delta 3 minus delta 1, x1 minus x3 delta 1 plus delta 3 minus delta 2. So this is the exact conformal 3-point function. But now I would like to take this 3-point function and I would like to expand it in the limit where x1 is going close to x2, in the limit x1 going to x2. So what am I going to find in this limit? Well, this factor goes to 0, so in this limit I'm going to get f1 to 3 divided by x1 minus x2 to delta 1 plus delta 2 minus delta 3. So this is the leading term. Now, in the same limit, there is no difference between x1 and x2, so I can group these two factors, and so the first factor has delta 2 minus delta 1, and this one has delta 1 minus delta 2, so this completely cancels, and I just get 1 over x2 minus x3 to the power 2 delta 3. So this is the leading term. So this distance to the power x to 3 to the power 2 delta 3 I'm getting. And then, of course, there's going to be corrections, but all these corrections are going to be suppressed. By what are they going to suppress? They're going to be suppressed by powers of x12 over x23. Let's say, let me write it like this. 1 plus corrections of this form. It's going to be infinite series of corrections. Now let's look at this. Let's look at this leading term. And this leading term has a very clear interpretation. So I can reproduce this leading term by saying that there is the following expansion for the operator product. So I can write O1 of x1 O2 of x2 equals f1 to 3 divided by x1 minus x2 to the power delta 1 plus delta 2 minus delta 3 O3 of x2 plus dot dot dot. So I'm saying here that in the limit when x1 going to x2 I can actually replace the product of two operators by instead at one of these 2 points. Okay, I chose here the point x2 for definiteness. So why is that? Well, because if I take this, so the way this OPE works is that I can take this expression and I'm going to stick it into the 3-point function. So I'm just going to replace this operator product by the right-hand side. And so if I do this, then I'm going to reduce my 3-point function to the 2-point function of operator O3 at the point x2 and operator O3 at the point x3. But this 2-point function is, of course, equal 1 over x2 minus x3 to the power 2 delta 3. So I reproduce the leading asymptotics of the 3-point function. Right, so it's very simple. Any so far so good? But now, what about all these subleading terms? There are infinitely many subleading terms in this formula. Of course, it would be it would be nice to reproduce also those terms. So the claim is that I can reproduce also all of these subleading terms. So this is called the leading OPE. And now, what I'm going to do, I'm going to add to the leading OPE. I'm going to say that, okay, if an operator O3 occurs in the OPE, then of course its derivatives are also going to occur in this OPE. That's absolutely natural. For example, if I take, I made here an arbitrary choice that I put the operator O3 at the point x2. I could instead have inserted it at the point x1. But the difference between O3 of x2 and O3 of x1 is by Taylor expansion and derivatives. Of course, derivatives are going to occur. With which coefficients? That we don't know. So what I claim is that I can add here an infinite series in derivatives of the operator O3. So I will have this d mu, then d mu d nu, plus, and so on. And I'm going to pick the coefficients of all these infinitely many terms in a way as to precisely reproduce these subleading corrections. So what's going to happen is that, okay, if I actually, let's go a bit slower, right? So suppose that I take this term and I stick it into the OPE. Now I have to differentiate the 2-point function of 303. So this is going to give me something which is 1 power, which decays at infinity 1 power faster than x2 minus x3 to the 2 delta 3. So it's going to decay faster. So for rotation invariance, I have to multiply it. Okay, so I'm going to multiply it by x12 mu. And here, here's going to be some numerical coefficient. And here is going to be x12 mu, x12 nu. Right? And so this gives me something suppressed by x23. And so I see that the scaling of this term is precisely of the same order as the correction we are trying to reproduce, x12 over x23. And so the claim is that I can do it order by order, and I can fix up all these coefficients in order to reproduce the 3-point function exactly. That's a claim. I'm not going to prove it, but it's a very plausible claim. And actually, there is an exercise. So if you look at equation 3.86 in my notes, in EPFL notes, then in that equation I give values for the first 3 of these coefficients, and I ask you to reproduce those values by doing precisely this matching exercise. So please do this. So so far so good. No, it's not crucial. No, but you see, okay, we can discuss what is the. So I'm not going to explain it to you in a lot of detail, but since you're a CF2 expert, notice that you know, so let's suppose that O3 is a quasi-primary. You know, you can consider the OPE by which includes also this L-2s acting, but provided that those will generate quasi-primaries different from O3, then the two-point function of them with O3 is going to be 0 anyway. So you don't, I mean, you consider those terms in the, but they're going to contribute to this three-point function. Going to consider two other three-point functions. So the answer is that it's true that in 2D you can consider this more refined OPE, which includes also L-2. But the way you should view it is that it's kind of a repackaging individual OPEs of this type that I'm considering. It's kind of a meta OPE, yeah. So it's kind of a very powerful way to group various OPEs together, which is available in 2D, but not available in 3D anyway. Yeah. Yes. Yeah. Yeah. So another comment, very important comment that I should make is that you know, this OPE expansion in the conformal field theory, it's not an asymptotic expansion, but it's really a convergent power series expansion. And this is clear because, you know, this expansion that I got for the three-point function here, it was convergent. It was a convergent power series expansion provided that the distance x12 was smaller than x23. So the radius of convergence of this expansion was x12 less than x23. And so the radius of convergence of the OPE I'm going to get by matching on this expansion is going to be the same. And this is very important because very often in quantum field theory, actually almost always in quantum field theory, you only use OPE to learn about the short distance asymptotics of certain correlation functions. And sometimes the short distance asymptotics is enough. For example, when you in the two-dimensional CFT, when you derive Virasoro algebra by integrating certain OPEs of the stress tensor, then it's not really necessary. So, you know, since you can choose the radius of the integration contour arbitrary, you are basically only sensitive to the leading OPE. But for what we are going to do next, it's going to be very important to be able to use OPE not just at infinitesimal point separation, but also at a finite point separation. And as long as you are within the radius of convergence, you can use the OPE. So that was one comment. And another comment, which is going to be natural, is that, okay, here I focused on the operator O3, but of course, you know, a more proper way to write the OPE is that I have to put here a sum over k, where instead of 3 I have to write here k, OK, and so on. So there's going to be infinitely many operators which occur in the OPE. And each with its own coefficient f1 to k. But if you're considering a three-point function with one particular operator, then of course you are sensitive only to the part of the OPE which contains this operator. Because when you take two-point functions of two different primary fields, it's going to be 0. So when you take this OPE and you plug it into the three-point function, then all terms are going to vanish except the ones where k is equal to 3. Right? So the OP is infinite. The OP is infinite, and a priori, we don't know any of these numbers. F1 to k, delta k. These are this CFT data, which are the ones that we are trying to determine. We don't know them. There is only one term in the OP which we do know, which is the term involving the unit operator. So there's going to be first term here. Let me write it separately. Plus 1 over. So here I'm going to sum over all terms except for the unit operator, and there's going to be one term which is which is going to be there only if the operators 1 and 2 coincide, delta 1, 2, and it's going to be, of course, 1 over x1 minus x2 to the delta 1 plus delta 2. So why do so this is a question too. Why do I claim that this term with the unit operator should be there? What requires me to put this term into the OPE? Because I need, exactly. Because I need to, the OPE is applicable in any correlation function. In particular, I can consider the 2-point function of operators O1 and O2. All terms in the first sum are not going to contribute because they are proportional to operators OK, which have positive dimension delta, and so their 1-point function is going to vanish. So so I have to have some term which is going to reproduce the 2-point function. That's going to be this term. So I can view it as something proportional to the unit operator, kind of as a bookkeeping. And the unit operator, of course, the derivative acting on the unit operator is 0, so all these terms are not there. Well, you could, but the point is that you could try, but it's not going to work very easily because these coefficients are very non-trivial functions of the operator dimension. So these coefficients are going to be some rational functions of delta, rational functions of delta k. And so, what you're suggesting to write something like e to the IPX d. Well, p is d, right? So ix12 d x, d, something like that. D acting on ox. This is, or maybe some other number a here, some vector a. So this would give us O of x plus a. So this would just shift. So this would be a trivial thing, right? But you will not be able to reproduce these rational functions of. So there is no room. These rational functions of delta k, they are not going to exponentiate, and so there is no easy way. So there are some explicit formulas for this whole series, but they involve some non-trivial integrals and so on. It's not. There's no easy repackaging. I think it's a good moment to make a break. Okay, ticked off OP, another item on our list. We are getting, yeah, we are going good speed, so we'll probably get where I want us to get. So the next item which we need to dominate is something which is called conformal blocks. So the idea is the following. Let's now take a 4-point function. So this is going to go in the direction that I mentioned at the very beginning, well, very close to the beginning, that while the conformal kinematics does not give us an expression for the 4-point function, which is fully fixed, because it gives us an expression which contains some function of the cross ratios u and v, which needs to be determined by some other means. I told you that in fact that function of the cross ratios can be determined in terms of the CFT data of the 3-point functions and the dimensions. So this is, we are getting close to how to determine that 4-point function. So the way we are going to determine it is by applying the OP twice. So we are going to take these two operators, and according to what I told you, we can write this product of these two operators, O1 and O2, as an infinite sum of coefficients f1 to k times, well, let me write it like this. It's going to be some infinite series P, which is going to depend on the point separation x1, 2, and it's going also to differentiate an operator OK inserted at the point x2. This is schematic. So in particular, there was some factor 1 over x1, 2 to the power delta 1 plus delta 2 minus delta k. This is all now sits inside this P. And this P, as I told you, it's completely fixed by conformal symmetry. So there is no dynamical information contained in it. It's a known infinite series which depends only on the space-time dimension, on D, and on the dimension of OK, and it may also depend on the dimensions of operators. So it depends on delta k and lk, of course, on the spin of this exchanged operator, on difference of the external operator dimensions, and on space-time dimension. So for this discussion, I'm considering the case when the external operators, so the operators whose 4-point function I'm evaluating here, are scalars. But I'm allowing for, this is of course possible. I just say I'm considering 4-point functions of scalars, but I'm even in the OP of scalars, there are going to be operators with spin occurring. For example, the stress tensor is going to occur in this OP. So here I have to allow for the possibility of operators with spin in the OP, but the external ones are scalars. And this function P, it so happens it can only depend on the difference of the two dimensions, delta 1 minus delta 2. I did not explain this, but that's how it works. And now I'm going to consider the OP of the other two operators. So these guys, so their OP is going to be sum f3 for k p x3 for delta OK of x3. So this 4-point function is equal to the correlator of these two OPEs. And so what this means is that I reduced my 4-point function to the 2-point function, to the sum of 2-point functions OK, OK, acted upon this horrendous derivative operators P. I wrote that I derived the expression that this 4-point function is equal to f1 to k, f3 for k, sum over k, infinite sum. The same k, because, okay, in principle it's not the same. Here it's sum over k prime, and here it's sum over k. But the 2-point function OK, OK prime is only non-zero if it's the same operator. So it collapses to, the double sum collapses to a single sum. P x12 d2, P x34 d3, x43 to be precise. Acting on the 2-point function OK of x2, OK of x3. So this formula solves the problem, at least in principle, because if I know all the dimensions of operators OK, and if I know all the OPE coefficients f1 to k, f3 for k, then by using this formula I can compute the 4-point function. And this expansion is going to be convergent by, I did not fully prove it, but it can actually be proven rigorously, at least for the unitary theories, that this expansion has a finite radius of convergence. But, in order to use this in practice, you need to work a bit harder, because what are these objects here? So there's a bunch of information here in this formula. So all this part, which depends only on conformal symmetry. So this term here, which multiplies which enters this, once you factor out the OPE coefficients, this term is called conformal partial wave. And just as in scattering theory, it's very useful to know explicit expressions for conformal partial waves. Also, in conformal field theory, it's good to have a good handle on these conformal partial waves. It would be nice to know them in as explicit form as you can, because basically, this is a complicated computation, and it's good to know it once and for all. It's good to do it once and for all. So what is known about these conformal partial waves? So one thing which is kind of intuitive is the following. So I told you in my first lecture, in one of my first lectures, that this 4-point function, it has the form 1 divided by x12 to a certain power, x34 to a certain power, times some undetermined function of the cross ratios. Now, it turns out, basically follows from conformal symmetry, that conformal partial waves have exactly the same structure as the 4-point function itself, except that this function GUV, which was undetermined for the 4-point function, for the conformal partial waves, it's completely fixed. It's completely fixed. And so if you take this expression for the conformal partial wave and you just put it here, then we get the following formula, that GUV is equal to the sum f1 to k, f3 for k, g delta k lk of uv, where this is the part of, it's the conformal partial wave stripped of this not interesting factor, which depends only on the distances. And so this factor is called conformal block. So there's some terminology here that I need to introduce. And so, basically, there is a technical problem at this point to develop methods for computing these conformal blocks. And, part of the reason there was a lot of progress in conformal bootstrap in recent years is precisely because people developed good control over the conformal blocks. So let me tell you what is known about these conformal blocks. Any questions about the terminology? So, first of all, what is the region in which these conformal blocks are defined? So recall that I think in my first lecture I was discussing that when we consider 4-point functions, then it's useful to fix the kinematics by sending one point to infinity. So I was sending 1 point x4 to infinity, and then two other points I was fixing at 0 and 1, which is distance 1 from the origin. And then there was a remaining point x2, which was moving in this plane. And I was saying that even if we are not in 2 dimensions, we are in d dimensions, we can still, so in this case there is just some rotation invariance around this axis, and we can still work on the plane. So in any number of dimensions, we can introduce a complex coordinate z, which is just the complex vector pointing from x1 to x2 in this kinematics. And the difference between 2-dimensional CFTs and higher dimensional CFTs is that in 2 dimensions, once you introduce this coordinate z, everything is going to be completely factorized. There's going to be things of z times of things of z bar. There's going to be holomorphic, anti-holomorphic factorization. If you do high dimensional CFTs, then no, there's not going to be complete factorization in terms of z and z bar. You will see some examples of that in a second, but still it's a possible and actually useful coordinate to work with, is z. We are allowed to choose any coordinate, so let's introduce this coordinate z. So the conformal block then is defined, is a function of z bar. So this conformal block g delta L becomes a function of z and z bar. And this function is smooth. Okay, it's not just smooth, it's infinitely differentiable and as we say, real analytic. So if we are in 2-dimensional CFT, then this function g delta L is going to be an analytic function of z times analytic function of z bar. In higher dimensional CFTs, it's not the case. So it's z and z bar are mixed, but still this function is a real analytic function, as we say, everywhere except for this interval, which extends from 1 to infinity. So so there are some singularities in this function on this interval, but if we were dealing with an analytic function, we would say that it has a cut there. Here we don't have analytic function, so it would be not correct to say that it has a cut. In particular, there is no notion of analytic continuation beyond this cut and so on. So it's just a place where the function ceases to be smooth. It has some singularities. So why does it have this? Why is it smooth everywhere except for here? There is a reason for that. And the reason is that the rule is as follows. So this conformal block is smooth every time you can find a sphere or a circle in this plane which separates the points x1 and x2 from the points x3 and x4. But this sphere does not necessarily have to be centered at the origin. So if you were allowed only to center the sphere at the origin, then you would conclude that the conformal block is smooth only in the unit disk around the origin. But that's not the case. So the sphere does not have to be centered at the origin, so it can be centered anywhere. And basically, approach this cut, not cut, but singularity, locus of singularities, then the radius of the sphere, which includes x2 but includes x3, becomes larger and larger, but it's still possible to find such a sphere. So this explains the singularity structure. So smooth except for z equals z bar belonging from 1 to plus infinity. Yes. Yeah, well, it totally break down. Yeah, well, it's not fully obvious that you can do, say, the OPE if x2 is here, because x2 is not closer to x1 than x3. But when I do the OPE, there is a certain freedom where basically what happens is that in this situation you could not do OPE in this geometry, but you could apply a conformal transformation in such a way that after applying conformal transformation, x2 is closer to x1 than x3. You would apply the conformal transformation where this sphere which separates x1, x2 from the other points is going to be mapped to the unit sphere. But if x2 lies here, then it's impossible to find such a conformal transformation, so things break down. It may look like you need it, but you don't actually need it necessarily, because if you apply the OPE for the points x1 and x2, you already reduced 4-point function to 3-point functions, and 3-point functions are known. So you don't necessarily need to apply that OPE. You could, but then you would have to apply, since x4 is at infinity, it's a bit difficult to understand what you mean by OPE. It's kind of OPE with respect to the infinity. Again, it looks like x4 is very far away, but you could apply an inversion transformation which maps x4 to 0, and then it's no longer far away. So in conformal field theories, what is far away and what is close is not always intuitive. Very important question, because what's going to happen is that my punchline is going to be that I can compute the 4-point function in 2 different ways, applying the OPE like I described, or applying the OPE in the opposite order, 1, 4, 2, 3. And is a consistency condition that two different OP expansions have to give the same result. And if you know some other things which this reminds you of, good, but these analogies are not necessary, strictly speaking. It's sort of associativity condition from the group theory point of view, that it's going to give us a sort of Jacobi identity for F. And this, in order to arrive at this Jacobi identity, you have to go to the 4-point function level. So at the level of 3-point functions, everything's fixed, everything is fixed by conformal kinematics, and there's no constraint. If you go to 4-point function, you discover this constraint, and then you can see that there are no further constraints by going to higher point function levels. So studying 4-point functions is both necessary and sufficient. And this is what going to constrain, so the consistency condition for the 4-point function is going to constrain the possible values of f's and deltas. So what do we know about this? What else do we know about the conformal blocks? I'm going to erase this. So these conformal blocks, they satisfy a certain eigenvalue equation. So let me write down this equation. So I'm going to state a bunch of results, and I'm going to state them only for the case when the external operators have an identical dimension. But in fact, all of these results extend also to the case of unequal dimension. It's just for simplicity. So for simplicity. So this eigenvalue equation has the following form. It's delta minus 1/2 C delta L G delta L Z bar equals 0, where C delta L is delta minus D plus L plus D minus 2. So I'm going to write down the equation and I'll explain where it comes from. And D is equal, so it's a second order operator, Z squared 1 minus Z dz squared plus minus Z squared dz plus Z going to Z bar. So it's a symmetric piece. And then there's a piece proportional to D minus 2, which makes things complicated. ZZ bar divided by Z minus Z bar times 1 minus Z dz minus Z going to Z bar. So there are these two terms. So this equation has a group theoretic origin. So it comes from considering the quadratic Casimir of the conformal group. So for every group you can consider, for every finite dimensional group you can consider a quadratic Casimir, which has the property that it acts when it acts on any full representation, it just gives you back an eigenvalue. So in particular, when it acts on a certain primary operator, or if it acts on a descendant of the same primary operator, it's the same eigenvalue. So every conformal multiplet gives you the same eigenvalue. And so you can compute the value of this Casimir operator just by acting on the primary. And we know how all the generators act on the primary, so you can compute the eigenvalue, and this is the eigenvalue. So it depends on the dimension and the spin of the primary operator. But now you can act with the same Casimir, not on the primary operator which you exchange in the OPE, on the operator OK, which is exchanged, but on the external operators O1 and O2. So O1 sits at the point x1, O2 sits at the point x2. So you have, when every conformal generator acts at the operator O1, it gives you a certain differential operator. On O2, another differential operator. So you just take this differential operator, you square it, and you act with it on the 4-point function. And so group theory tells you that that the contribution that this conformal partial wave is going to be, when acted upon by this conformal Casimir operator, is just going to be an eigenfunction with this eigenvalue. So this is the reason. But now you know the form of the 4-point function. I wrote it. It's a function of uv, right? And so when you act on this function of uv with this complicated conformal Casimir differential operator, it spits out this equation in terms of z and z bar. So this is not a fully trivial computation, but it can be done. So the result looks simpler than the intermediate steps. As you see that this result, it has two pieces. The first piece is completely factorized in terms of z and z bar. And this operator, actually, it's a hypergeometric differential operator. So if we just had this piece, which happens in d equal to 2, you see, when the second piece is proportional to d minus 2. So in d equal to 2, we only have this, and we have full factorization. So in that case, the conformal blocks would be just hypergeometric functions 2f1s of z times 2f1s of z bar. So let me write it down. So in d equal 2, conformal blocks are just g delta L's, are just of the form 2f1 with certain arguments of z times 2f1 of z bar. If you go to d larger than 2, then then we have the second term to deal with, which is a bit annoying because it does not have full factorization. It's, you have an antisymmetric numerator divided by antisymmetric denominator, so it's a smooth operator, but it's not factorized. And in that case, it's hard to find exact solutions, but actually in d equal to 4, again, you can express them. So there's going to be something like 2f1 of z, 2f1 of z bar minus z going to z bar divided by z minus z bar. So such an answer works and gives you conformal blocks in d equal 4. So it's possible. So in d equal 3, which is the case interesting in for the three-dimensional easy model, it was for for a long time it was unknown how to get exact special function expressions for these conformal blocks. And it's only very recently, actually, it's last week, there was a paper, very interesting paper by Isachenko and Shomeros. So it's very recent. I did not have a chance to study it myself yet. But what they found is that they found in general D, they found expressions for these conformal blocks in terms of virtual Kornwirth polynomials. I know, first time I hear this name, but apparently polynomials. So it's again some special functions, but very complicated special functions. But in practice, even though, okay, modulo this very recent result, which we have to study better. So in practice, what we were doing so far, we were using the fact that these conformal blocks, they have extremely rapidly convergent power series expansions. So what we were doing so far for our computations, just to take, to generate these expansions, up to the first 100 terms, which we can do, and then this would provide accuracy with 100 digits, which was much more than what we needed for the numerical values of these conformal blocks. And so that's what we were using so far. So in fact, the way you generate these expansions is, so no, before I go, let me say one more thing here. So I told you that these conformal blocks, they have they satisfy these differential equations, but in order to solve a differential equation, you need to know boundary conditions. And the boundary conditions for the conformal blocks, they are provided by the OPE. So boundary conditions so if you take if you consider Z equals if you consider the small z limit, then the conformal block has the following asymptotic: G delta L of ZZ bar equals absolute value of Z to the power delta times C L nu of cosine alpha, where this plus dot dot dot, where this guy is what is called a Gegenbauer polynomial. So nu is equal to d over 2 minus 1. So this polynomial is okay. It's so in d equal 2. This is just these are just usual cosines of L alpha, just trigonometric harmonics. And in d equal 3, these are Legendre polynomials. And in general, D is this Gegenbauer polynomials. So basically, so the conformal block, it comes from the exchange of the primary and all of its derivatives. If you ignore the derivatives, if you just take the primary, then you generate this term. And all the derivatives, they will come suppressed by extra powers of Z. So you're supposed to solve this Casimir eigenvalue equations with these boundary conditions. Yeah, sorry guys, I realize that it's getting probably very technical, but unfortunately that had to happen at some point. So any questions? My goal at least is to make sure that you are following the logic of what's going on. So maybe not the details, but at least the logic of this journey should be clear. So if the logic at some point becomes vague, then please immediately interrupt. Otherwise we'll get lost. So what do you do in practice? In practice, it turns out, as I said, that there are these very efficient power series expansions. And actually the way you generate these expansions is in a slightly different coordinate frame. Let me write it down. So there is this coordinate row, which is equal to z divided by 1 plus square root 1 minus z squared. So the reason why this coordinate is interesting is that as we said, conformal blocks are defined in this plane of z, where you have a singularity from 1 to plus infinity. Now it turns out that if you apply this transformation, this complex mapping, then you map this plane with this cut, you map it to the unit disk. Absolute value rho less than 1. So this whole cut gets mapped to the boundary of the unit disk. And 0 is mapped to 0. So that's why it's a nice coordinate. And if you write it as r e to the power I phi, then again conformal blocks have an expansion in which the first term is equal r to the delta, rather 2r to the delta, times the Gegenbauer of cosine phi, and then there are suppressed terms. And the reason why I consider this expansion is that this expansion to the first order in Z agrees with this expansion. This is to see to the first order in Z they agree, but it turns out that so this expansion represents a sort of partial resummation of that expansion, and it turns out that in this resummed form, the contributions of the emitted terms are much smaller. So this is kind of a smart partial resummation. So you still need to include many terms in this expansion. So when you do like state-of-the-art 3D-using model conformal bootstrap computation, you include hundreds of terms in this expansion. But if you were to do it in that form, you would have to include many terms, many more terms. So use it like this. And then, so in practice, we have an efficient way to generate this expansion, and that's all. That's all what we need. And to finish, I wanted to show you a few plots. I think I'm not going to explain you how we generate this these subleading terms. Actually, one way to generate these subleading terms would be just to take this expansion and to stick it into the Casimir differential equation, and then just solve the Casimir differential equation order by order. This would allow you to generate this expansion to as many terms as you want. There are smarter ways to do this, but at the practical level, you don't really need to know this. You can read about it in the lecture notes. But so that you have an idea what is the level of the difficulty that in the end of the day, once you learn all these tools, I want to show you this Mathematica notebook where with just 10 lines of Mathematica, you don't have to do it in Mathematica, but here just for illustrative properties. So this code, it realizes a recursion relation, which is an efficient way to generate this power series expansion. So you see here, there's this variable r, which is the variable that I have here, and then there's a variable eta, which is cosine phi. You see, the only reason why I'm showing you this is to convince you that it's no big deal. That if you ever need to write a code which computes these conformal blocks for you, it's just 10 lines. You basically take, this C1, C2, C3. You take them from a paper. There's some Pochhammer symbols. It's really nothing, not at all big. You see here I have a Gegenbauer polynomial, which is what I wrote here. So this PL8 is the Gegenbauer polynomial. So it's really not a big deal at all. And then, so what I'm doing here is that I want to compute one particular conformal block. So I take the conformal block of the epsilon operator in the three-dimensional Ising model. So the epsilon operator in the Ising model has dimension roughly 1.41. Of course, we now know it with many more digits. But let me take here for the illustrative purposes 1.41. And I evaluate the conformal block for the dimension equal to delta epsilon and for spin 0 because epsilon is a scalar, and I only compute the first 12 terms in this power series expansion for the purposes of this exercise. And here are these 12 terms. You see, it starts with 1 because I take the factor r to the delta out already. So everything here is multiplied by r to the delta, and then I have an expansion in powers of r squared. And you see this. So this is the contribution of the primary. It's 1, and then I have contributions of descendants. So primary in this case is a scalar, but descendants, some of the descendants are scalars, other descendants have spin. For example, at level 2, so r squared means it's second derivatives. At second level, I can have a scalar and I can have a spin 2 field. So spin 2 means that maximum spin 2 means that it's going to be a polynomial of at most second power in eta. And indeed, I have a certain degree 2 polynomial in cosine phi in eta. Then at level 4, I have a fourth degree polynomial and so on. So I have this expansion. Any questions about this? And then I just want to plot these things. So I'm plotting here. So this was not the full conformal block. It was the full conformal block where I factored out this r to the power delta epsilon. And there was also some other function factored out, which is just a fixed function. And so what I plot here, in this unit disk rho less than 1, I plot two things. So on the left, this is the contribution of the primary. So this is just r to the power, delta epsilon, the first term. And on the right, I have the full conformal block. Well, not the full, but the first 12 terms. And what I wanted you to see is that if r is small, if I'm close to the origin, then of course the primary contribution approximates the conformal block very well, but as you move further away to the boundary of this unit disk, then of course you have to take into account all the contributions of the descendants. And as I'm going to explain next time, the actual value of R important for the conformal bootstrap applications is equal to 3 minus 2 square root 2. So there is going to be this magic value, which is approximately equal to 0.17. So there's going to be a reason for that. I'm going to explain it next time. And so this number is not exactly 0, but it's also not particularly close to 1. So it sits somewhere here. And what it means is that the series I was showing you, converges near this point extremely rapidly. So you do have, if your goal is to reach high precision, to compute the critical exponents of the 3D Ising model with many, many digits, then yes, you have to include many terms. But if your goal is just to get a rough estimate for these critical exponents, then you don't even need to work so hard. But as I said, including these terms is not difficult anyway, so there is no reason not to include them. Any questions? So this was for the scalar. Now let me show you, I still have a few minutes, so let me show you the same thing for the stress tensor. So here I'm doing exactly the same computation, but I'm computing it now for the stress tensor, which means that the dimension is equal to 3. We are in 3 dimensions, and the spin is equal to 2. And again, I'm computing 12 terms. So this is the polynomial which it spits out. You see that now the first term here, which is this, so this is in fact the polynomial, the Gegenbauer polynomial is in fact the Legendre polynomial of for the spin 2 exchange in 3 dimensions. And then there are again contributions of descendants. So if you plot the same plot as I did before, so this is the contribution of the primary. You see now, since I'm dealing with a spin 2 primary, there is some angular dependence. So there is a dependence on the angle. If I also include the contributions of descendants, then roughly the angular dependence is roughly the same. So as I say, the descendants, they don't do much, but there is some, for precision studies, there is a little bit of deviation, of course. Yes. Which coefficient is not 0? You mean that this is 0? So this means, this means indeed that you could interpret it indeed as a the stress tensor is a conserved field, so its multiplet has a bunch of fields which are 0 just because of the conservation condition. So probably the fact that this coefficient is minus 10 to the minus 17, which means it's 0 exactly, is related to this. So, but from the numerical point of view, you don't worry about this. Well, it's 0, it's 0. So in fact, indeed, even though the stress tensor is conserved, actually the conformal block of the spin 2 field varies continuously with delta. So you start from delta equal 3, which is the stress tensor, and you vary delta, and the conformal block varies continuously. So those new states which appear as you move from delta equal 3, they appear but with a very small coefficient, so they don't cause a discontinuity. So as I say, the goal of this demonstration was just to show that it's really not a big deal. You can do this. I think I'll stop here.